All right, let's dive right in. We're talking about Nature's Blueprint, the hidden science of building. And yeah, it's a pretty wild idea. We're going to look at architecture that takes its cues not from industry, but from biology itself.
So here's the big question, right? In a world where the weather is just getting more and more extreme, how do you actually build a house that can survive intense heat and crazy powerful winds? Seriously, how do we make our homes tough enough for what's coming without, breaking the bank or the planet?
For a long, long time, the answer was just brute force. Just throw more steel and more concrete at the problem. But what if that's not the smartest way? What if there's a much more elegant solution out there? What if we started learning from the OG engineer, the absolute master of resilience and efficiency, nature? Okay, to really get this, we have to totally change how we think about a building. We need to stop seeing a house as just, well, an object, a static box, and instead start thinking of it as a living, breathing system, kind of like a biological cell.
Think about it. Every single living cell has this protective layer, a membrane. And it's not just a wall, it's this super intelligent barrier. It's constantly deciding what gets in and what gets kicked out, all to keep the environment inside perfectly stable. And that single idea, that's the key to this whole thing. So boom, there's the connection to architecture. Just imagine a building's walls doing that exact same thing, protecting you from the crazy heat outside, but still letting the whole structure, breathe.
And get this, it's not just some cool metaphor. This is real. When you build with natural stuff like rice straw or cotton fibers or clay, the wall literally acts like a cell membrane. It's selectively permeable. Air can slowly pass through for ventilation, but it blocks that intense heat from getting in. The result? A super stable, super comfortable temperature inside.
Okay, so we've got this awesome living wall. Great. But how does this cool biology idea actually stand up to, the laws of physics? How does a house like this not just fall over?
The whole secret is a concept called static equilibrium. Sounds fancy, but it's pretty simple. It just means that every single force acting on the building, gravity pulling down, wind pushing from the side, the ground pushing back up, they all cancel each other out. They're in a perfect balance. When all those forces add up to zero, the building doesn't go anywhere. It just stands there.
And this whole thing is basically Newton's third law in action. Remember that one? For every action, there's an equal and opposite reaction. So the wind pushes on the wall, that's the action. In response, the structure of the house pushes back with the exact same amount of force. That's the reaction. As long as that internal pushback matches the external push from the wind, the house stays put. It's so simple, but wow, is it powerful.
So you might be wondering, how do engineers actually make sure all those forces are balanced? Well, they use this really cool tool called a free body diagram. It's basically a sketch where they can zoom in on one piece of the building, say a single wall or a beam, and draw out every single force that's pushing or pulling on it. It's how they spot the weak points and figure out exactly where they need to beef things up.
All right, so we've talked about the biology of the building's skin and the physics of its skeleton. Now, let's grab a microscope and zoom way, way in. We're going to go down to the molecular level to see the chemistry that makes these natural materials so unbelievably strong.
So, what does make these natural plant fibers so strong? I mean, think about it. You see plants and trees bending like crazy in the wind, but they don't snap. What's their secret? Well, the answer comes down to one of the most basic building blocks in the universe.
The hero of this story is the carbon atom. See, it has 4 electrons in its outer shell that it loves to share, which makes it the ultimate connector. It's amazing at forming these super strong, super stable bonds with other atoms. And that lets it build these long, long chains, which are not only the foundation of life itself, but, as we're finding out, the foundation for some seriously tough buildings.
And when you link all those carbon atoms up, they form these long chains called cellulose. And honestly, the best way to think about cellulose is it's nature's rebar. The steel rods they put in concrete? This is nature's version. It's what gives plant cell walls their structure and provides this incredible strength that we can borrow for our own buildings.
What's really neat is that different plants use the cellulose in different ways, so we get this whole menu of amazing materials to work with. Take rice husks. They're super low density, full of tiny air pockets, and since air is a terrible conductor of heat, they make for fantastic insulation. Then you've got cotton stalks. You can press those into panels that are incredibly strong. And things like palm fibers, they're lightweight and flexible, which is perfect for handling forces like wind.
Okay, so we have biology, we have physics, we have chemistry. We've got all these amazing principles.
The big question now is, how do you actually combine all of that into a modern building plan? Well, that's where technology comes in and builds the bridge.
Before anyone even breaks ground, we can build the entire house digitally. With software like SketchUp, you can create this perfect 3D model. You can slap on textures to see exactly how the straw or clay will look. But here's the really cool part. You can run simulations. You can see how the sun will hit the house at different times of day, study the heat and the shade, and tweak the design to make it as cool and efficient as possible.
So here's the real takeaway, the big idea. True innovation, the really powerful stuff, it's not about finding one single magic bullet solution. It's about connecting the dots. The absolute best, strongest, and most sustainable solutions come to life when we weave together ideas from biology, physics, and chemistry. That's when you create something truly special.
And that kind of leaves us with one last big question to chew on. If we can completely rethink how we build a house just by studying a tiny cell, what could we do if we scaled that thinking way, way up? What could our cities, our massive, sprawling cities, learn about energy and resources and resilience from a forest? Now that is a question worth thinking about. Thanks for joining me.